Hi everyone, so here we are on day number 2 for acids and bases, and this is going over what we call the pH concept. Okay, so you have probably heard of pH before, probably in science throughout, the years, especially middle school and stuff, but now we're going to talk about the pH on the mathematical scale. All right, so here is your equation for pH. The negative log of the concentration of H+. Okay, so it is a log function. And so for an example, if you have the concentration of H+ to be 1 times 10 to the negative 1, then the pH is just going to be 1. Okay, so notice if it's 10 to the negative 2, then the pH is 2 because you're taking the negative log of it. So notice that the pH is basically just the exponent, but since you take the negative log of it, then it becomes positive. Okay, now that only works if this number in the front here is a 1. If the number in the front is not 1, then you will actually need to plug this into your calculator to get a more accurate answer for your pH. So what pH stands for, it stands for the power of H. Okay, that's why we're taking the negative log of the concentration of H+. There is an equation that's also similar to this one, and it is for POH. So this would be the power of hydroxide. So that would be the negative log of OH minus. If you wanted to find the inverse of the POH, so if you wanted to find, for example, the concentration of OH minus, then it would be 10 to the negative POH. And then if you wanted to find the H+, then it would be 10 to the negative pH. Okay, so I will help you with your calculators using your log key and your inverse log key to do these problems, and we'll have more practice doing this. Just one more thing about the log function here. So the Richter scale is also based on a log function, and when we're dealing with, especially for acids or bases, we're dealing with these really, really small numbers. And so when we are dealing with these really small numbers, it is just easier to use a log-based function, so then we can just look at bigger numbers. Okay, so it just makes things a lot easier. I mean, imagine if they said, oh, the earthquake was a 5.7 times 10 to the negative 8. Like, nobody would understand what that meant. So by transferring the Richter scale to a log function, and then when people say that, oh, there was a 4.5 earthquake, then people kind of understand that magnitude and what that means. All right, so this is just the equation stuff for pH. Now, if your pH is less than 7, then it will be an acid. Okay? If your pH is greater than 7, right, it's going to be a base. Then, of course, if your pH is equal to 7, then it will be neutral. So this is just review for you because I'm sure you have learned this in middle school before. This is just the pH scale. All right, so once again, remember that you have both ions in solution, H+ and OH-. And it just depends which one is in higher concentration that will determine if your solution is an acid, a base, or if it's neutral. So if I draw a line here, okay, notice that this whole area would be shaded in red. Remember, red represents acid. And then this small section here would be shaded in blue. So since most of it is acidic, then also notice here, right, anything less than 7, then it will be an acid. If you had drawn that line like, right down the middle, then it would be equal red and equal blue, or equal H+ and equal hydroxide, and that's how you get a neutral solution. If we were to draw the line on this side where it is greater than 7, then you can see why it would be basic, because all this area here or that whole entire section would be shaded blue, which represents hydroxide, and then just a small section shaded in red for the H+. Now, these are just some examples of household items that you are familiar with and where they fall on the pH scale. All right, so we know things that are less than 7 are acidic. So hydrochloric acid, which is a very strong acid, notice that it's like practically 0. That is very, very acidic, okay? Stomach acid, we know, is also very acidic, so that's a 2. Lemon juice. Vinegar is a weak acid, but it's still acidic, and that's like a 3. You go up here, we are almost at 7, looks like 6.5 is milk. Notice milk is slightly acidic, okay? And so have you ever heard of sour milk? That's what happens to milk when it gets old. It tends to sour. And then, of course, pure water is 7. Blood is slightly basic. Ammonia, household cleaner, we talked about that the other day. Remember, that's NH3. It doesn't have hydroxide in the formula, but it is a base. It's a weak base. And then here we have sodium hydroxide, which is a very strong base. Notice it is at the very top of your pH scale. Okay, basically saying that it is very, very basic. All right, so there are different ways that we can actually measure pH, okay? We had talked about litmus paper. Remember litmus paper, if it's acidic, it turns red. If it's basic, it turns blue. Now, there are other pH indicators out there. For example, there are other ones that will change color. Like a common one that we're going to be using in the lab when we get back from spring break is phenolphthalein. We're going to do a titration when we get to chapter 21, and this is an indicator that we will use. It changes color. It changes like bright pink when it's basic, and it's like colorless when it's acidic. Phenol red, if any of you have a swimming pool at home and you check the pH, one of the indicators you will use to check the pH is phenol red. Now, the most accurate way to measure pH is to actually use a pH meter that has a probe on it. It will actually give you a digital readout as to what the pH is. Like it'll say the pH is, 8.47, so it gives you an actual number. Whereas all of the other ones are colors, and we're trying to compare colors on a color chart to kind of estimate what the pH is. So once again, the pH meter is the most accurate way to measure pH. Okay, this is just review going over the Arrhenius definition of acids and bases. And we had talked about this before. Basically, if it's an acid, it gives you the hydrogen ion in solution, okay, H+. Don't forget H+ and H3O+ are equivalent to each other. If it is a base, according to the Arrhenius definition, it gives you hydroxide in solution, which is OH-. Now, we also might classify acids as being mono, di, or triprotic. So protic refers to proton. So what is the proton in this chapter that we have been talking about? H+, right? Okay, so this part's not that hard. Sulfuric acid, look at the formula for sulfuric acid, H2SO4. Notice that there are 2 H's in that chemical formula, so we say this is diprotic. Okay, this acid is diprotic. Then look at the phosphoric acid, H3PO4. So there are 3 H's there, so this one is triprotic. Okay, has 3 H's or 3 protons. That's why it's called triprotic. Now I'm going to go over the Bronsted-Lowry definition for acids and bases. So this is different than the Arrhenius definition. So according to Bronsted-Lowry, acids are going to donate a hydrogen ion, and then the bases are going to accept the hydrogen ion. Okay, the hydrogen ion is H+. All right, so acids are giving up an H+, and then the bases are accepting the H+. So now I'm going to go over an example of this so that you can better understand the Bronsted-Lowry acids and bases. Okay, so for the Bronsted-Lowry, let's write down this equation, HF plus water. This will give us H3O plus and F minus. So what we're going to do for the Bronsted-Lowry acids and bases, on the reactant side here, one of these will be labeled the acid, one will be labeled the base. On the product side, one will be labeled the conjugate acid, and then one will be labeled the conjugate base. Okay? So between HF and H2O, which one should we label as the acid? That would be HF. So then we would label the water as base, because you have to have one acid and one base on each side. So according to the Bronsted-Lowry definition for bases, water is going to behave like a base. I'm not saying water is basic. I'm just saying according to this definition, the water will act like a base. Okay? Then what we're going to do is, let's take a look at HF. It's going to be paired with one of these things that's on the product side. And we know how to pair them correctly because their chemical formulas will differ by an H+. Okay? So that's why the HF will be paired with the F-. You see how those two, look at their chemical formulas. See how their chemical formulas differ by an H+. So if this is the acid, then that means that the F- is going to be labeled as its conjugate base. Okay, it has to be an acid-base pair, and then on the product side, those are the conjugates. Then if this is the conjugate base, then that means H3O plus is going to be the conjugate acid. Okay, so you can see how those two are going to be paired. You see how those differ by a hydrogen ion. So that's how I know that those are going to be paired up together. Okay, remember it has to be an acid-base pair. All right, we're going to do one more example. NH3 plus H2O gives us NH4 with the +1 charge and hydroxide. All right, so we're going to label these acid-base, conjugate base. So let's take a look here. NH3. Now, it doesn't have H+ in the front, and it doesn't have hydroxide in the formula. So some of you may not know if this is an acid or if it's a base. NH3 is actually a base. It's a weak base, and that is something you should recognize as being a base. Although it doesn't have hydroxide in the formula, it is a base. Ammonia is found in Windex. So if NH3 is a base, then that means our water is an acid. Notice in this case, water is behaving like an acid, okay? Whereas in the previous example, water was behaving as a base. So notice water can be either acid or base. And we say that, there's a term for that. We say that water is amphoteric, okay? Amphoteric. Like amphibian, right? The prefix amph means both. All right. Now, what if you didn't know that NH3 was a base? I'm going to show you how you can work backwards to figure it out. Well, look at your product side. We notice right here we have hydroxide. Okay, hydroxide is what? Acid or base. That represents a base, right? So since it's on the product side, then this would be the conjugate base, therefore this would be conjugate acid. Okay, then you would notice that you would pair those two up together. See how those differ by an H+. And then you can see how these would be paired together, and those differ by an H+, okay? So notice base with its conjugate acid, acid with its conjugate base, okay? Has to be an acid-base pair. All right, so that is everything for this section. I am going to write down on the next slide a whole bunch of equations for pH and everything else that you should kind of keep all in one place. Just so you have all your equations in one area, in one section, so they're easy to find. Okay, so let's write down all of these pH equations that you're going to be using. So the first one that we learned before was the KW equation. H+ times OH minus. Okay, and then that is going to equal 1 times 10 to the negative 14. Then we have our pH equation. pH equals negative log of H plus. And then you have one that's similar, but it's POH, right? Negative log of OH minus. And then you have the inverse of those equations. So then if you want to find H plus, is the second log to the negative pH. And then same over here, if you want to find the hydroxide, is the second log to the negative POH. Okay, and then another one that's helpful is pH plus POH will have to equal 14. So what we're going to do is we're going to use all of these equations here, and we're going to practice solving for H plus, pH, POH, and all of these things. So this is part of your worksheet, and we're going to do some of these examples in class. All right, so I will see you later. Bye.